Thank you. So I'm Francesc Campoy, and today I would like to talk about program analysis. Just a little bit about me. I work at Google. I'm a developer advocate for the Google Cloud Platform, and I've been working with the Go team for the last 3 years or so. So the goal of the talk is to talk a little bit about what program analysis is first, and go over the two different kinds, static analysis and dynamic analysis. And then basically the whole thing is I had some ideas, and to talk about those ideas, I have to give a lot of context. So the whole talk is going to be basically giving context about tooling and things you can do. And then I will propose something that I think can be interesting for some people. OK, so what is program analysis? Program analysis is basically extracting information from a program. And that information can be many different things. One thing could be correctness. So is the code doing what I expect it to do? Or robustness. What happens when something goes wrong? Are we handling the errors? Is this everything correct? It's just going to panic and fail completely? Also, we can have information about performance. Not really how to improve it, but where's the point where performance is not that good? So basically, how to find a bottleneck in our performance so we can fix it afterwards. And then there's all the things that you can imagine about a program. So this can be pretty much anything. You can imagine programs to detect if something is idiomatic, or if something is well documented, or any other things, basically. And the key factor here is that program analysis is done by a machine. So if you're reading the code, that's also program analysis, but that's not what I'm going to be talking about today. So as I said before, there's two kinds of program analysis, dynamic and static. And we're going to start talking a little bit about dynamic analysis. Dynamic analysis is when, given a program, the thing you do is you run it, and you see what happens. And to do that, there's two things that have to happen. One is you actually run the program. And the other is sometimes, not always, you instrument the code to be able to observe some things. And there was a talk by Dimitri at GopherCon, Go Dynamic Tools, which is an awesome talk. If you haven't watched it, or if you were not at GopherCon, I recommend it a lot. OK, so let's see some of the things that we can do with dynamic analysis. One of the things that I consider to be dynamic analysis, it's unit testing, which is kind of a weird thing. But what we're doing is we're extracting the information about the correctness of a program by writing more code, basically. So in this case, for instance, we're verifying that the sum function, given a slice, returns an integer, returns what we expect. So if we pass the slice 1 to 3, returns 6. That kind of makes sense. There's another thing that I consider, too, to be dynamic analysis, even though we tend to forget about it because it's the default in Go, which is every single time you access a slice, a position in a slice, actually not every single time, but sometimes when you access a position in a slice, there's that check that it's happening. And it's basically making sure that the memory that you're trying to access is part of the slice. If it's not, it will fail. So in this code, for instance, there's a bug. I don't know if you can see it. It's after food, but there's coffee, so maybe you see it. There's nothing here. So our for loop is going from the positions 0 to the length of the slice. So that's an off by 1 error. Too bad. If you run this, and you run the code passing a little slice, so the elements 1, 2, 3, by default, it will fail. It will panic, saying, hey, I'm sorry, you tried to access position number 4 in a slice with 3 elements. I cannot do that. But if you remove the bound checks, which you can do with gc flags equals -b, then the program runs. And it works, kind of. You will actually get 10, because it will do 1, 2, 3 plus 4. accessing that piece of memory is technically correct because it's part of the same program. So the OS won't stop this. So that's also kind of analysis of our program, making sure that it's correct by adding instrumentation. Another tool that does pretty much the same, but it's much more complicated or complex, is the data erase detector. The data erase detector, what it does, it instruments every access to memory to make sure that if two Go routines are accessing the same piece of memory, they're doing it in a correct way. So using some kind of protection, such as a mutex. So in this code here, what I'm doing is something that is completely wrong. Of course, it's called race detector, so that's obvious. What I'm doing is I'm creating this counter. And with the first Go routine here, what I'm doing is every second, I increment that counter. And then I have another Go routine that 5 times a second will print the value of n. And if we run this runs, and it works, which is kind of surprising. Now, the problem is that if you put this in production, at some point, it might fail randomly, and it will be way too late to find this bug. So how can we find it? Well, we can run tests, or we can even build and generate binaries that have that instrumentation on every single memory access. And here I can do it too. And you will see that as soon as we get to the first time where we're actually modifying the variable while reading it, we get a warning, actually, that will print exactly the lines where we were accessing and what were the Go routines that we're trying to modify at the same time they were accessing. Let me kill it. Otherwise, OK. OK, so all of this was about making sure that the program does what we think it does. But what about making sure that the program does it as fast as we want? So there's different tools for this. And how many of you know what the sieve of Eratosthenes, super hard to pronounce, is? OK, most of you. So basically what we're doing is we want to know all the prime numbers. Well, not all of them, because that's impossible, but we want to have n prime numbers. The way we do it is we start with an empty, it's going to go empty now. There we go. We start with just all the numbers that we have, just the list, and we start with 2, and remove all the multiples of 2. Then the next number that has not been removed is also a prime number, which is 3. We remove all the multiples of 3. Then the next number that has not been removed is 5, and so on. So we're doing this continuously, and we end up with just the prime numbers. Now, the interesting thing is that you can also do this concurrently. And this is actually from an article that Russ Cox wrote. And this was one of the first pieces of concurrency that I actually saw in Go. Basically, what we do is every single prime number is managed by a Go routine. So what we say is, OK, this Go routine is the one managing the filtering of all the multiples of 2. This one, all the multiples of 3, and so on. And then what we do is we just pass a number and wait to see if it actually goes through all the filters. If it goes through all the filters we had, it's a prime number, and we create a new Go routine. Cool. I'm not going to show the code. And if you want to see the code, it's actually online. It's really really easy to find. Actually, if you Google concurrent prime sieve without saying it's Go, the first result will be Go, at least for me. OK, so let's try to understand what this program is doing. As Andrew mentioned before, one of the things that we can do is run pprof. And pprof, what it does is basically it allows you to dump a profile of either CPU or memory or locking. And once you've dumped that that output, then you can visualize it with the tool pprof. So in this case, what I'm doing is, OK, I'm going to dump all the CPU profile for my program. And I'm actually running the program run. The function run is the one that runs the prime sieve. So once I do this, I obtain an SVG file that then you can open. And you can see that 66% of the time, we spend our time filtering, which kind of makes sense because That's pretty much everything we're doing. We're generating some numbers and seeing if it's filtered or not. And out of that 66%, most of the time, we're actually either sending or receiving channels. So this could be maybe a way to improve it. Could be maybe there's a better way, rather than using channels, of having something slightly faster. You can see that most of the time is channel receive, channel send. So that's where you could try to concentrate on, fix the performance issues, if you had any. Dimitri, in his talk at GopherCon, he also talked about this tool. And this tool is pretty impressive. I used it for the first time after GopherCon, and I decided to talk about it today, because I was pretty impressed with it. So basically what it does is it takes every single event that happened in the Go runtime and logs it. So Go routine, if we create a Go routine, we start it or we end it. If a Go routine blocks or unblocks, if we do a system call, if the garbage collector starts, any of those events are logged. And then using I think it's the same one, but I'm not completely sure. I think it's the same visualizer that Chrome uses to visualize the rendering of CSS, JavaScript, and so on. We're able to generate a very beautiful log that will actually contain all the things that are happening in your program. So to generate a trace, you don't even need to change anything. You just do go test-trace and the output, and that will generate two files. Trace.test, sorry, which is the test binary. That's just a Go program, basically. And then the trace.out, which is the output of our program. If we run this, you will get something like this. And now, here what we can see is, we can see the size of the heap, except that it doesn't change in this case, so you cannot see much. But you can see how many Go routines we have, how it's going up and down, how many threads we have, and then for every single processor in my machine, you can see where we're executing stuff. So you can see that we have Go routines. Every single one of those colored boxes is a different Go routine that is running there. And if you zoomed in enough, then you could see that actually those things actually have a number, G20, that's Go routine number 20, and what's the function that it's running. So in our case, it's trace.filter. So it's the filter function of our trace package, which is part of our code. So with this, you can have a pretty clear idea of what your program is doing. But then you can also zoom in into one single Go routine and see how it interacts with other Go routines. So basically here, what you could be able to see is how the values are being sent from one Go routine to another through channels, and how that creates contention across different Go routines. So basically with this, you could be able to understand the code without having to read it, which is kind of the point about program analysis. There's many other tools that are considered dynamic analysis. Code coverage is one of them. Debuggers are kind of one of them, except that they're interactive, but they're pretty similar to what other tools do. And I'm sure there's many others. If you have any that you think that I've forgotten completely, I'm sorry. And just let me know. I'm really interested about the topic, so just let me know. I want to learn more about it. OK, so as a conclusion for the dynamic analysis section, the good things about dynamic analysis techniques is that, in general, they're actually pretty simple to implement. So implementing the bounds check, that's actually really simple, right? So that you have to check that it's between 0 and length -1. Pretty simple to do. If you're implementing the data race detector, not that easy, but still doable. And it finds issues that are actually occurring, because if you are trying to access a position in memory, only when that position in memory is not correct, our analysis will fail. Now, on the other hand, only the problems that are occurring will be detected, which means that you're actually not completely sure that you're detecting all the errors. Even for the data race detector, you're not 100% sure that you're actually finding all the possible errors. What's the solution for that? Well, running it for longer. But the problem is that you're actually generating a binary that is slower than a production binary, because you are instrumenting all the access to memory and so on. I could argue that that's totally fine, and you should always have one of your binaries built with the database detector and many other dynamic analysis tools that is running in production but getting shadow traffic. So if it crashes, you get a beautiful log telling you what happened, and you can then fix it. Much easier to do that than then trying to find out what happened on that server that actually was running in production and crashed randomly. OK, so now we're going to be talking about static analysis. And if in dynamic analysis what we're doing was running the code and see what happens, in static analysis, we don't really run the code. What we do is we analyze the code itself, and we try to extract information from it. So there's no need to instrument any code. And actually, there's not really an impact on performance there's no impact in performance of the code executing it, like for performance, the performance cost that you get from instrumentation, because there's no instrumentation at all. These run aside from production. This is completely different. And unlike dynamic analysis, where it's really hard to prove a property because you're not sure that you're actually going through all the possibilities, at least in Go, since we have access to all the code that is available for a binary, we're able to prove things. We're able to actually say, this will never happen, or this will happen always, which is important. Not for all properties, of course. There's properties that are not computable. OK, so tools that are part of this static analysis family. All the Go star things. So Go thumped is one of them. Go thumped is actually going through your code and trying to find all the places where your code doesn't match the conventional formatting. If it doesn't match, there's two things that it can do. Either just emit a patch difference with -d, and then you can consider it as static analysis. Or you could just rewrite the output directly. And that's not really analysis because you're modifying the output. It's more a transformation, but it's pretty much the same. You also have GoLint. How many of you use GoLint? OK, around 50%. So GoLint is this little tool that will give you warnings that will annoy you most of the time, but actually is things that you should really fix. So there's things like, if you have a variable name called sum_value, you will get a warning telling you, this is not Python. You should write camel case. And if that some value starts with a capital S, we'll also say, and you should always document exported identifiers. So these are things that are really more like, you should be doing this. The code is completely correct. But if you want to have high-quality code that any other Gopher will look at it and feel familiar, GoLint will help you doing that. GoVet, it's a similar tool, but rather than finding slightly things that are not conform to the norm, it's more about finding possible errors. So if you have a call to printf, and the string has 3 parameters, but you're actually passing only 2, then probably there's an error there. So it will tell you. If you have a mutex, and you pass it, and you copy it around, that will also let you know, because when you copy a mutex, there's no synchronization going on anymore. So that's most probably an error. So GoVet will let you know about these things. And finally, we have GoDoc. And GoDoc, it's basically just going through all the code, finding all the identifiers, and all the documentation attached to it, and just displaying it in a readable format, a human-readable format. And then it's kind of not static program analysis anymore, because you're actually reading code now. But you're reading the code that you care about. So I could say this is also a kind of analysis. Other tools. How many of you know error-check or error-check? OK, not many. This is a really cool tool, and basically warns you when you're ignoring an error implicitly. That means that in this case here, os.remove, removing a file could fail. So that actually returns an error, but I'm ignoring it. And I'm ignoring it implicitly, meaning that if you write that code and then I'm the code reviewer, probably I might forget that remove returns an error. So that might be a bug. Error check will let you know, and let you know that if you want, you can then ignore it explicitly, and the warning will leave. But then you're writing underscore equals something, and you should feel really bad about writing code like that. And that's the point of really enforcing you to have a higher quality of code. There's also something that you can do only with static analysis, which is analyzing code that is almost correct. It's impossible to do with dynamic analysis because it doesn't run, doesn't compile, doesn't run, so you cannot do it. And it's really useful for people like me. So I consider myself a lazy programmer. The least I have to write, the happier I will be. So the first tool that is obvious is Go imports. And I'm assuming that Go imports is basically known by everyone nowadays. What it does is it will find all the import paths that you are. So if you import a package, but you don't use it, that's a compilation error in Go. So it will actually find those and just remove the import statement. So that way it doesn't fail. But if you're using a package and you're not importing it, it will add the import path. And now that's interesting, because what it does is it will find a package in your Go path that matches the name and that has an identifier that matches the identifier you're using. So if you write http.get, it will actually find that that's the net HTTP package. So this makes your life easier, coding in general, much faster. But there's some limitations, such as, where is template.template defined? There's actually at least two places that have it. There's text template and HTML template. Which one is the one you want to use? Go imports doesn't know that. And it's normal, because you might want to use one or the other. Most of the time, it's going to be HTML template, and I think that most of the time, Go imports will say text template. So it's something that you learn to live with. But if you know a way of fixing that, it's an open source project. We accept PR, so. Then there's Go returns. And Go returns, as far as I know, started as a joke in Speaker's Dinner in .go last year. And basically, the joke was someone saying, like, oh, yeah, I'm too lazy to write when you return an empty string and an error, or a 0 and an error. It's like, it'd be awesome if a tool did that for you. You can do that. And it's actually now a tool that Quinn from SourceGraph created. So it's installed in my machine, but I always forget that I have it, so I think that it never runs. But if you want to do something like that, it's something that you can do. And then yesterday, at the speaker's dinner, again, another great idea happened, which is Ben, which is now giving a talk on the other track, mentioned that he had an issue with when you define a local variable and you don't use it in the same function, that's also a compiler error. And he was not happy with that. So I proposed the name govars, and you can create it if you want to. I don't think that this exists yet, but it could be really simple to go over all the variables that have been declared but not defined, and either remove them, or comment them out, or add just like a fake usage so the compiler is happy with it. I don't think this is a good idea, just letting you know clearly. But if you really feel the pain, it can be a fun project to work on. OK, so let's see. All the tools we've seen so far for static analysis are based on three kinds of techniques. We have lexical analysis. And lexical analysis, it's basically just extracting tokens from code. So this is the kind of thing that will detect a string that never ends, or a comment block that never ends, these kind of things. Doesn't do much. I don't think there's any of the tools that I mentioned that is based only on lexical analysis. We also have syntactic analysis. And syntactic is more about the grammar of the language. So this is more about you cannot use a range statement unless you're in a for loop, or these kind of things. or you're going to use an else unless there's an if before. And then there's type analysis. And type analysis is the one that it's the most important for many tools. So for the most of the tools we've seen so far, syntactic is enough. But if you want to understand better what the program is actually doing, so if you want to know what's the type of a given expression, syntactic analysis is not enough. Actually, you could build it on top of syntactic analysis, but then you could be reinventing the wheel. The type analysis does that for you. And there's a list of packages that from the standard library that do these kind of things for you. So we have Go Scanner and Go Token for lexical analysis, Go AST, so abstract syntax tree, and Go Doc that extracts the documentation, and also type analysis. And for type analysis, Go Types, which is part now of Go of the standard library too. And with this, you can do all the tools we've seen so far. But the question is this enough? So let's see this code here. So the code you can see here is a really bad piece of code. I think we all agree with this. But I would like to ask the question, what's the value that this function returns? What are the possible types that I could get? All the information that I'm able to say is, well, empty interface. Or maybe, if I'm smart enough, I could say it's either nil, or a string, or a float, or false. But actually, what I would like to be able to do is be even smarter than that and realize that if n is 42, then it's an even number, so it's impossible to return a float. Can we do that with everything we have so far? Well, no. Why? Because we're actually understanding the syntax and the types, but we're not understanding yet the values of the possible values that a variable can have. So when we want to do that, that's what we call data flow analysis. And data flow analysis is basically just a family of algorithms. There's a lot of different things that you can extract, and they follow the flow of a program. And once you have the flow of a program, actually the other side of it is also what are the possible values for a variable. If you know one, if you have an if statement, you need to know the value of that expression to understand the flow. And there's things that you can do with it, such as finding dead code. Finding dead code is something that you can do with just Go types, but you can do with data flow analysis. You can also find common expressions. So basically, a common expression is if you're using x plus 1 multiple times in your code, I would like to compute it only once, if possible. That kind of thing, you can do it with data flow analysis. And there's a family of algorithms for this. And they're sometimes quite complicated. But there's a form of a way of representing code that makes those algorithms simpler to implement. And that's why it's called single static assignment intermediate representation, which is super long, so SSAIR, or SSA for short. And this is something that has been talked. So Ben Johnson gave a great talk at GopherCon, again, about SSA and why it's important and how he uses it. And basically, SSAIR, it's an intermediary representation, meaning that it's just a different way of representing Go code, nothing else. But it has one specific constraint, which is you cannot assign to one variable more than once. So that means that once you have a variable defined and it has a value, you cannot modify it anymore. And when you do this, all of a sudden, data flow algorithms are easier to, basically, once you have this, understanding the code is much easier. So there's this book that is actually still not finished by Indria, which is a French university, well, no, department, I guess. And they define SSA as a program is defined to be in SSA form if each variable is a target of exactly one assignment statement in the program text, meaning that you can assign exactly once to each variable. So if we have this code here, a equals 0, b equals 1, and b equals a plus b, that's not SSA, because b is being assigned twice. Cool. Can we fix this? Well, yeah, we just add indexes to every single variable. So now a is a1, and the first b is b1, the second b is b2. That's it. Now it's SSA. Why do we even care about this? Well, from the same book, this is actually from the same book, and I really liked it. So if now I say Homer, what do you think about? Homer Simpson? I'm assuming most of you. Some of you might think about other things. I think about Homer Simpson because I like The Simpsons, and you should also like it. What if I say Homer, but also say mermaids? Now you're going to maybe think about another Homer. And what's the problem here is that just a name is not enough. Names are not unique. And that makes us deal with different, with having to deal with context and ambiguity. And Go has the same issue. So if we have x is 1 and y equals x plus 1, and then we change the value of z, and then z equals x plus 1. What is the value of x? The answer is, well, it depends. The value of x where? Or a similar question is, are y and z the same value? Well, they're both equal x plus 1, right? So they could. But they're actually not, because x has different values. Once you have SSA, that problem disappears. If y equals x plus 1 and z equals x plus 1, y and z have to be equal, because there's no way you can have different values for the same variable. And this is what it's called referential transparency. So referential transparency is basically the fact that once you have one name, you always know the value behind it, regardless of the context or situation. And you can enforce something similar in C++ by using const, or the final in Java. Not the const in Go, though. It's a different thing. And how many of you do any kind of functional programming? And how many of you do functional programming and have never heard about referential transparency? Yeah, it's a big thing in functional programming. But it's also something that applies to SSA. And it makes reasoning over the problem much easier. OK, I'm not going to get into much detail about how, like, all the concept of SSA. There's books about it. Like, it's a really vast topic. But the interesting thing is, OK, so how do we use it? We have two packages which are not part of the standard library, are part of the tools repository. And they're both written by Alan Donovan, which is right there. So if you have questions about SSA, he's the man. And there's two of them that I've used. The first one is SSA. And SSA is a package that contains all the building blocks of the SSA representation. So basically, for every single statement in Go, for every single kind of instruction that we have, you will find a different type. So you have the type return, the type switch, the type for loop. All of those types are actually types. So you can basically get all of those and build a form, an SSA form of your code. And SSA dump, what it does is exactly that. Given a Go program, it generates an SSA representation, and then it dumps it. So given this code here, which is factorial, which is already, now it's not really SSA, is it? It could be. But what I'm doing is I'm going to dump it as SSA. And this is the output. And when you see it for the first time, it's kind of scary. But then, if you pay a little bit attention, you will see that it's actually quite simple to understand. Every single variable has been renamed. Actually, the name of the variables have been removed completely, except for the parameters. And every single variable now it's just T0, T1, T2, and so on. So that way, we're sure that we're not reusing any variable. So what we're doing first is we're comparing x to 0 as a type, as a value, as an integer value. And then, depending on that value, we go to either the block 1 or the block 2. If we go to the block 1, we just return 1. If we go to the block 2, we compute that expression that we had there, x times factorial of x minus 1. And we do it in every single value is a different intermediary variable. Now, the important thing about this is that once we have this, understanding this code, it's much simpler. The possibilities of what you can find in an SSA program is much smaller. So the code will be longer, but it will be much simpler to interpret. Also, you can see already that we have blocks, and you can also find the transitions between different blocks. We know that from 0, we can go from 1 to either to 1 or to 2. And once you have that, that's what it's called a CFG, a control flow graph, which is something that you will need to understand to do pretty much every single data flow analysis. So for Go 1.6, there's a plan of actually using SSA to build a new backend for Go. So we'll be able to generate Go code directly from SSA. And the goal here is to have better generated code. So once we have SSA form, we'll be able to perform a bunch of different optimizations that right now might be too complicated to perform. So we should be able to remove dead code better. We should be able to remove common sub-expressions. And also, we should be able to use better memory and registers. So pretty excited about that. We'll see how it goes. There's a link. I will share the slides, and then you will click that link if you want to. OK, so now this is the worst pun of my talk. So be ready for that. So what are the tools enabled by SSA? There's not that many, but there's one that I want to talk about more. Really? So it's called the Oracle. So you really don't watch the Matrix? OK, so the Oracle is a source analysis tool, and it's something that we use from an editor. If you try to use it from the command line, you're going to have a bad time. It's really hard to do, and I tried. It's not worth it. Just use it with either Vim or Emacs or any editor that you like to use. And it's powered by both SSA and also pointer analysis. And I'm not going to get into detail of what pointer analysis is. I'm sure that the Oracle design document explains pretty well, gives links to what you need to know more about it. But basically, it will allow you to know, given a variable, what are the possible values behind it. So let's do a little demo. Oops. OK, so I have some code here. Let's remove this for now. And so I have two functions, foo and bar, and I'm calling them from main. So I can come here and ask, what are the colors of this function? And incredibly hard, it finds that it's right here, foo. That's it. That's the only place where you're calling it. That's pretty simple. OK, what happens if now we have slightly more complicated code? Now what we're doing is we have the same two functions again, but rather than calling them directly, we are calling do and passing a function as a parameter, and then calling that function. So will this work? Well, if we do again the same thing, and we ask what are the colors for this function, it will again say, now it's main.do. Before it was saying that it was a static function call, meaning that you were calling the function by name, and that's the only function you can call. Here it's a dynamic function call, meaning that it depends on the execution. if that function or a different one will be called. But we know that that function will be called at least once in there. Even cooler, you can actually ask, OK, so what are the functions that might ever be called in here? And that is not Go colors, it's Go colis. And it lets me know that that f can be either main.foo or main.bar. And this sounds like, sure, that's easy. But if you actually have a big program, being able to do this kind of analysis can be really useful. So let's see a slightly bigger program. Oh. So this is just a very simple HTTP server, like really, really simple. But I can go to one of the handlers and ask for the same thing. Who's the caller of this? And it will tell me that it's the net HTTP package at some point calls it. And I could go and navigate and try to find how it calls it and so on. But also I can do something which is pretty impressive because it really feels like it's not static analysis anymore, which is I can ask for the call stack. And when I do this, I'm actually trying to find a way to go from the main function to this given function. And it's not running the code. So this is still static analysis, even though it looks like it's dynamic. So you can see all the function calls in there, going from our main.main at the bottom to main.hello on top. And now, one of the side effects of Go not having an implement statement is that it's hard to tell all the interfaces that a type satisfies. So Go Oracle also does that. So you can do Go implements on this type person. It tells me that there's two types, fumpt.stringer and runtime.stringer. Runtime.stringer is actually a non-exported type, so you don't really care about it, but Oracle finds it anyway. Even better, you can do things like, oh, so I have my error interface, which is just basically an error interface. Find all the errors in my Go path. And there you go. Now you can see these are all the errors in my Go path. There's not that many. That's sad. But basically, you're going to be able to navigate your code much easier with this. Something cool is that GoDoc also does the same thing. So you can execute GoDoc with dash analysis equals pointers. And then you will get these implements here. And you will find all the types that implement that interface. And also, all the interfaces that this interface satisfies. So I can go here, os.file. No, wait. So reader, for instance. And we can see all the readers in the standard library. So that can be pretty useful, especially because this will do it. If you run it on your machine, it will do that analysis on your Go path, not only on the standard library. OK, so now we've seen a bunch of different tools. And some of them are useful for navigating your code. Some of them are useful to understand performance. Some of them are useful to understand the validity or correctness of your code. But there's a thing that I would like to do, which is, as a speaker, very often you get to say things like, oh yeah, this is a best practice. You should always do this. And when you say things like that out of the blue, it's hard to justify. Like, why is this why is this single idea a best practice? So I think that it could be great if we use static analysis to test our best practices. So let's see an example of this. There's a best practice that I think we'll agree with, which is you should always have the narrowest interface possible. So in this case, if we have dump2 and you're dumping to a pointer to a file, that works, but it's hard to reuse. So rather than doing that, it could be much better if you just pass a writer, because then your code does the same thing, but it's easier to reuse and easier to test. So this actually, there's a talk, if you're interested about this kind of best practices, Jeremy Sainz gave a really good talk at .go about this topic, and this is actually part of the inspiration for this. So can I write a tool to do this? And the answer is yes. So basically what I do is, for every parameter in every function, I go and find every single usage of that parameter. And I see if it's used as a concrete type. So if I'm getting one of the fields, that has to be a concrete type. If I'm accessing some position behind, it has to be a slice or a struct or an array. If we're calling it, has to be a function, and so on. But if you're just calling methods on it, then you don't really need a concrete type. It could be an interface. So all of this can be achieved with Go types. And I actually implemented this. And I implemented this, and then I was like, cool, I'm going to run it on my code and prove that you should always use the narrowest interface. So I had tests like this. If you're accessing a field, yeah, that has to be a struct, so don't say anything. If you are accessing one position, if you're indexing that, has to be either a map or a slice or an array. But if you're doing something like this, handle, and you're using con as on println requires a writer. So rather than doing handle con, could be a writer instead. Cool. I wrote this, and it worked. But then when you run it over all your code, you find this, which is HTTP handler. And all of a sudden, you realize that most of the time, you use response writers as writers. So of course, you should use just an IO.writer, not a response writer. Then you do that, and your code doesn't compile anymore. Ouch. OK, so what's the solution? Well, I actually need to understand where and how I'm using this value. So we have the same problem with handler here. A handler is now a struct and defines a method serve HTTP. And it's a method, but if we change any type in that method, then we're not satisfying the interface anymore, so it doesn't compile anymore. So that's kind of sad. So what's the solution? Well, we have to find all the places where that function is called, or all the places where that given type that we're considering modifying is used, and then all the interfaces that a type satisfies to make sure that once we change something, we're actually not satisfying less interfaces. And it turns out that the Go Oracle is able to do this. So the only problem that I had is Go Oracle is supposed to be a tool for navigating your code, not really a library. So I had to fight a little bit against it, so that's why it's still not open source. One day, maybe. I have to talk with Ellen. But it's pretty much implemented, and it works. So my flow for this was, OK, so if I describe a best practice, I can say, always use the narrowest interface. But then when I translate it to a program that actually tries to enforce that, I will find counterexamples. So there's a solution for that. Either I ignore them, I fix my code because my code was not correct, or I fix my best practice because my best practice was not correct. And I think that this is something really useful. Like, before you try to say, you should always do this, because that's the best way to do it, try to write a tool that enforces on your own code, and try to find out if you're actually following your own best practices. And I think we have some time for questions, I guess. OK, so thank you.